I always like to describe momentum as inertia while moving. It's not the definition you'll see in the book, but it's what it really represents. A really large object with a small velocity can have the same momentum as a really small object with a big velocity. Look, a bullet only weighs a couple of grams. The bullet's not dangerous. It's the bullet's momentum that's dangerous. It's because it's traveling at hundreds of meters per second. That's what makes it dangerous. It has a lot of momentum. Momentum is a really simple calculation. We use a lowercase p for momentum. So if there's a line on your paper, the p should be there. Okay, lowercase p. It's just the product of the mass and the velocity of an object. Now, just understand, velocity is a vector quantity. It's not squared here or anything. That means that the momentum takes its direction from the velocity. I mean, the momentum of an object is in the direction it's moving. Now, the next couple things I'm going to do they're mathematical. They're designed for you to understand where all of this is supposed to fit in. So, for those of you who are not particularly mathematical, I will sum up in a minute. But for you guys who have a little bit of a mathematical flair, this might appeal to you. If you have not figured it out yet, physics is all about change. Change in position, change in velocity. Everything that we tend to talk about is about how something changes. And the thing that causes those changes are forces. We developed an entire concept of energy based on the idea that a force is what causes the change. That forces change an object's energy, and they do so by doing work. Momentum is another side of the same coin. Although momentum looks similar to kinetic energy, there are important distinctions between them. Energy and momentum are not the same. They are not the same. To totally understand what's happening, you actually need to observe both. Meaning, in a real system, we need to know both the energy and the momentum to make real predictions of what's going to happen. And that's because there are different ways in which these interact. The good thing to know is that although there are lots of different kinds of energy, there is only one linear momentum. If an object has momentum, there's only one type that it will have. If it's moving, it's got it. If it's not moving, it doesn't. Now, we knew that changing an object's kinetic energy occurs because work is done. Net work causes a change in kinetic energy. It was a big topic last time. We saw that because of our definition of work. We put that definition in there, if you'll recall. We talked about this is always due to an unbalanced force. That was the question about the rocket that many of you got wrong. An unbalanced force changes an object's kinetic energy. It does net work, but it requires an unbalanced force. If there's an unbalanced force acting on an object, then we know the object is going to accelerate. And because it's accelerating, we knew that we could use a motion equation to describe this. We remembered that v final squared minus v initial squared equals 2a delta x. Well, I see the a delta x there. And so through substitution, I was able to show that 1/2 m v final squared minus 1/2 m v initial squared equals delta k. We did this in class to demonstrate the work energy theorem. Now, the change in something's energy was based on how far the object moved. If you'll recall, almost everything we talked about was about changes in position. In fact, one of the questions you had to do with recognizing when the object had the biggest change in height, because that was when the object had the biggest change in kinetic energy. Do you remember problem number 1 in the test was the object on the string, and it was dropped. And you're asked between what 2 points was there the biggest change in kinetic energy? And it was the first 2, because the height was the biggest difference. There's a lot of things when we talked about work that were about change in position. Momentum, we're going to take a little different tact. We're going to go back to the idea that nothing changes without there being an unbalanced force. That's an unbalanced force that causes changes. But if an object accelerates, we know that the direction of acceleration is based on the direction of the force. We didn't talk about direction over here. And part of the reason we didn't is because the velocity ends up being squared here. All that directional information goes away. But on this side, I want to take that directional information to heart, because I know that acceleration is defined as the change in velocity over time. Another way to consider acceleration. So I could rewrite this as the net force equals m v final minus v initial over t. Now if I distribute the top, I get m v final minus m v initial all over t. Now, I don't know if you see this, but mv final would be the final momentum, and mv initial would be the initial momentum, which means I could write this as the net force equals P final minus P initial all over T. This is the first consequence I want you to know about momentum, is that Newton's second law is actually about momentum, not about acceleration. Newton's second law, as Newton wrote it, was that net force is the rate of change of momentum. This is Newton's second law. Knowing this isn't super important, I don't think. I like my students to have a historical perspective. I want them to understand that Newton had big ideas in mind. He knew that inertia was really intertwined here and didn't want to be bound by objects that had constant mass. He realized that masses change, objects break into smaller pieces, stuff like that happens. He wanted to anticipate the big things that were happening in the universe, which is why he actually wrote, is anybody in here in calculus? Because he actually writes this as net force equals dp dt. Remember, Newton invented differential calculus, not integral calculus. So almost everything that's in physics can be written as a differential. It's Leibniz who came up with integral calculus. But the differential calculus that Newton comes up with was to support his belief that everything in physics was about rates of change, which is why so many things in physics are about differentials. Now, that part's not huge. The next thing is the most important part of the lesson today. What I'm going to do is what I want you all to know. So those of you who I said, this is really mathy, you can kind of check out, you need to come back for this. What going to multiply both sides by T, okay? To the left side, net force times T. Right side, delta P. This is the most important thing you need to know today. This is called impulse. Impulse and work are two sides of the same coin. Impulse is to momentum what work is to energy. I would put that in your notes. So, impulse is how you change something's momentum. Work is how you change something's energy. Impulse is how you change something's momentum. Just so you know, this is kind of important. You're not going to like this, but generally, a force that causes an impulse likely also does work because they're both forces. It's hard for a force to act without moving something. So both are changing usually at the same time. But impulse tends to be more suited to things that happen fast, while work tends to be more suited to things that happen slow. Things that are falling through the air, great. That's probably a good work question. Things where you hit an object with a bat, that's probably a good impulse question. Now, I want to divide this in half and make sure you understand that there is a cause and effect going on here. Because there's only one kind of momentum, it's not like we're transforming the energy from one type to another. When we do work, we're changing the type of energy the object has. But when we're doing impulse, we are merely changing the momentum. So the effect of an impulse is physically looking at the final momentum compared to the initial momentum. This can be in 3 dimensions if necessary. While the cause of the impulse is the size of the force and how long it acts. Now, trust me when I talk to you about this, when you deal with the concept of impulse, sometimes it's hard to understand what they're getting at. But you can calculate the impulse on an object either way. Meaning, if you have information about its velocity, then you better use the effect way of calculating impulse. If you have information about force, you better use the cause. I'm saying this because if a question just asks for impulse, either side of this equation will do. You don't need both. But they're going to try and be confusing. So here's a starting question. This is a basic get us started kind of question, okay? Right back there, change in momentum's the right side. So it is the impulse. It's the effect side. You drop a ball above the ground. The ball hits the ground going 10 meters per second. It bounces off the ground going 7 meters per second. If the ball has a mass of 0.5 kilograms, what was the impulse on the ball from the ground? Now listen, folks, I used a lot of words there. They were not accidental, they were deliberate. I asked about the impulse on the ball from the ground. Because of Newton's third law, there is also an impulse on the ground from the ball. Anytime two objects interact, there are two impulses. Just like in our prior chapter, anytime two objects interact, there was two amounts of work done. So remember, due to Newton's third law, there are reciprocal impulses. So the impulse on the ground from the ball has got to be the same as the impulse on the ball from the ground. Impulse obeys Newton's third law. But impulse is directional. When I ask for impulse, I am asking for two pieces of information. The number part and the direction. So in this example, do me a favor, decide for me. This arrow that I'm drawing right now, is it pointing the positive direction or the negative direction? All right, so up is positive. That's helpful, isn't it? Because if I want to calculate the impulse with what I've been given, what I'm actually going to do is calculate the change in momentum. Because change in momentum is impulse. That's what it says. So right here, I have the final momentum and the initial momentum. The final momentum has to do with the bounce of the ball upwards off the floor. To calculate that, that's going to be the mass of the ball, 0.5, times the speed of the ball, 7. But I also have to take into account direction. You said that up is positive, so I have to put positive here because it bounced upwards off the floor. Next, I'm going to subtract the initial momentum of the ball. The initial momentum of the ball has to do with the mass of the ball, 0.5, times its velocity, which was 10. But it was traveling downwards before it hit the ground, so its initial velocity was negative. Remember those motion equations where we had to take into account direction every single time? We're back to that all the way. But that was it. When I asked for the impulse, the answer is going to be whatever the result is here, which, based on my recollection, 0.5 times 7 is 3.5, and 0.5 times 10 is 5. So the negative times the negative means that this will be 3.5 plus 5, or 8.5. And it is positive. Now, units are going to be important, as always. And to get this, we had to take kilograms and multiply by meters per second. So the unit of momentum is the kilogram meter per second. And there is no special name for that. The unit of momentum is the kilogram meter per second. But wait, there's more. But let me pause. So the ball was in contact with the ground for 0.02 seconds. The ball was in contact with the ground for 0.02 seconds. What was the force on the ground from the ball? This is a trick question. And I don't know if you're really paying attention or you just like acting like you're paying attention, but it's a trick question. I'm purposefully trying to trick you. So I'm telling you that I want the force on the ground from the ball. Here's the trick. This is why you really need to be paying attention to me, because I do this on purpose. And I'll do it on your next test on purpose. We found the momentum change of the ball, which means we found the impulse on the ball. And it was positive. This must equal the force on the ball times the time that the ball is in contact with the ground. This is the force on the ball. Now we can find that because I said that it was in contact with the ground for 0.02 seconds. So, moving all that up so it's easier to see, force times 0.02 seconds equals 8.5. Positive 8.5. So if I want to figure out the force, and please do, somebody be a kind person here and tell me that, what is it, 425? Let's look at those units. That would be kilograms, meter per second divided by seconds. Do you know what unit that is? Let me rewrite it. Maybe this will help. 425 kilograms, meters per second per second. Do you know what that unit is? What is it? That's not the unit. What do we call this unit? Kilogram meters per second squared. Come on, Lauren, please. That's right. 425 newtons, yeah. By the way, this is not the answer. This is the force on the ball. What did I ask for? I asked for the force on the ground. If you want the force on the ground, what would you have to do? What's that? I'm not getting the answers I wanted. I'm a little disappointed. If the ground had to push up on the ball to get it to bounce upwards off the floor, what direction did the ball push on the ground? Down. Yeah, the actual answer would have to be negative to indicate this is the force on the ground from the ball. The ball pushed down on the ground. It had the same impulse on the ground from the ball. Newton's third law. When you find one impulse, you have found two. You want a big thing for the front of your notebook, a big thing that you should write down to make some of this stuff you're going to have to do easier, something you should put in a banner location at the front of your this chapter? There are always two impulses. When you find one, you have found two.